Okay, we are going to finish Chapter 6 today, even though I'm not there. If you fall behind on the notes, just let the sub know to hit pause till you catch up. And we're going to finish up. We're going to be doing confidence intervals again. This time we're doing confidence intervals for population, variance, if you remember, it has the symbol sigma squared, and a confidence interval for population standard deviation, which is just sigma. Okay, so we're talking about maybe making pills for medicine, and when you make the pill, you want your machine to have very little variance in it. You want those pills to be as exact in weight with each other as it possibly can. So you would keep measuring that. So when we do confidence intervals for variance and standard deviation, the distribution of these two is no longer normal. Okay, now the weights are normal, but when we start to look at variance and standard deviation, that's a different distribution. It's called a chi-square distribution. So for variance and standard deviation produce what's called a chi, Greek letter chi, and I'll show you what it is in a minute, square distribution. Okay, the Greek letter chi looks like a big fancy X. That's chi-square, that's just our squared power. So a chi-square distribution has a couple of properties. Unlike the normal distribution, chi-squared values are always greater than or equal to 0. So all chi-square values are greater than or equal to 0. So we have no negatives here. So they're not symmetrical. And the curve is defined by degrees of freedom again. Curve is defined by degrees of freedom. And just like the other day, our degrees of freedom are going to equal sample size minus 1. Area under the curve equals 1. And the shape of the distribution is skewed right. So if we were to graph variances, all variances from our sample or all standard deviations, we're going to get a graph that starts from 0 and goes out, and it's skewed right. So that means you've got more data at the beginning, tailed to the right. Okay, so when we do our confidence interval here in the next example, we're going to need to find our critical chi-squared values. Now I know the old calculators do not have this ability, but I don't know about the new ones. I don't think the new ones have this either. I think this whole section has to be done by hand. So in our first example, we're going to find our chi-squared values. And like I said, this is not a symmetrical graph, so we're going to be finding what they're calling chi-squared left and chi-squared right. Well, obviously we're talking position on the number line. So your chi-squared right is the one that's farther out on the number line. Chi-squared left is going to be the smaller of the two numbers. Okay, and now I'm going to show you how to read the table to get these. So our first example is finding the critical chi-squared values. Okay, the chi-squared table is only in one spot in the book. It's on page A21 in the back, and we'll go there in a minute. Our first example, let's say we were doing a 95% confidence interval for the population variance we had a sample size of 25. Okay, and sample size does not matter here because we're going to know that the data is normally distributed. Like if I was doing weights, the weights would come from a normally distributed population, but when I start doing variances of standard deviation, that's where this skewed comes in. So they're coming from normal populations, so I don't need that magic number of 30. So 25. So with just this information, you should be able to find the two chi-squared values. Okay, and it's all based on area and degrees of freedom. So if I just do the rough sketch, I'm looking for those two chi-squared values. I know there's 95% of the graph in between those two chi-squared values, and I still have an equal amount in each of these pieces here. So that's 2.5% in each one. Okay, let's go take a look at the chi-squared table on page A21 in the back of your book. And remember, if you're falling behind, just have the sub hit pause and continue on when you catch up. All right, A21. Okay. I want you to look at our chi-square table. And when we read this, it would have been nice if they were consistent, but they were not. The chi-squared values, you're going to look up here. We've got degrees of freedom here. And then we've got this alpha. And what alpha is it's your total area to the right of your chi-squared value. See how they've got this graph shaded to the right? We're kind of focusing on this. So when I look back at my graph, if I want this chi-squared value, which is the chi-squared right, so for chi-squared right, I would look up the area to the right, which is the 0.025, and my degrees of freedom, one less than the sample size, 24. So if you go to the table, you want area to the right, which is 0.025, and down to the 24. So my chi-squared right is 39.364, if I'm on the right line. Yep, 39.364. So 39.364. Okay, remember these are not symmetrical like our other ones, so we do have to look this one up. This is not a negative 39.364. They're all positive, remember. This number line is starting at 0. So it should be smaller than the chi-squared right. So chi-squared left, the area I need to look up is the total area to the right. So take a look. How much area, if I'm standing here, how much area is to my right? Well, it's 95 plus the 2.5. So that's 97.5%. So you're going to look up the 0.975 and same degrees of freedom of 24. One less than the sample size. Oops, sorry. So the area I wrote down was 97.5% total area to the right. And then degrees of freedom. Like I said, everything we've done with the inv norm and the inv t, we needed area to the left. Now they switch gears and make you go area to the right. So chi-squared is the one we want area to the right. The other ones we want area to the left. So looking up 0.975 and down to 24, 12.401. So make sure you can find that. 12.401. And those will be the two critical values that are going to be used in the formulas that are coming up. Okay. So chi-squared, area to the right. All right, so the confidence interval for population variance. We'll go with variance first. Okay, and it's just a little plug and tug formula here. You're going to go n minus 1, which is your degrees of freedom, times your standard deviation from your sample squared, which is your variance from your sample, divide by the chi-squared right value. Because remember, the right, because this is going to be the small end of my interval, so I want the bigger number down here. If I divide by a bigger number, I get a smaller outcome here. And then the upper end is n minus 1 times that standard deviation squared. Bottom is chi-squared left. So they switch places when I actually do the interval. Okay? And then the confidence interval for population standard deviation. Well, remember, what's the relationship from variance to standard deviation? And again, you're not here to answer the question, but remember, we just take the square root of this to come down to sigma. So all we're going to do to get the interval for standard deviation is take the square root of these two answers. So it's going to be the square root of that answer we got up there. So the square root of those. And then we'll have the interval. Okay, let's try one. Let's see, try it number 2. Okay, let's see. Find population medicine weights. I gotta go back. Okay, you're gonna randomly select 30 samples of allergy medication. It's allergy season, so select 30 allergy meds, and you're gonna find the weight. And the standard deviation of your sample was 1.2 milligrams. Assuming that weights are normally distributed, but remember when we take the standard deviations, that's what makes our skewed graph. So weights are normal. Construct the 99% confidence interval for population variance and population standard deviation. So we're doing two intervals, but they're connected. Okay, so again, like I said on